Um, uh, Also, so folks, if you a few logistics. So I'll be monitoring the chat for questions. You should also feel free to like raise your hand if you have a question. But otherwise, we ask that please to stay muted during the lecture. Um, Other than that, I think so we're not going to be sort of announcing the sending reminders for every single lecture. But it's going to be at the same 11:30 a.m. US Eastern time each time. Okay, and I think with that, let's hand it over to Anton. So please, Anton, get us started.
Thanks, Steve. Hi, everyone. I have to admit, I haven't been this nervous in many, many years for teaching, but hopefully it will go away. Okay, so first we're going to talk about some administrative things, and let me hide this part. Administrative things. Number one, this class is going to be like a deep math class. That's what it's going to feel like. We're going to do everything by like written notes. I tend to go a little bit fast when I'm writing on my iPad, and I'm going to work on slowing myself down, but I want the audience to slow me down too. I want you to be liberal with your questions. You can, put it in the chat or interrupt me if Ziv or I miss it, whatever. So be liberal with your questions and don't be shy, especially for the PhD students. Um, I make mistakes. I'm going to give the caveat that everything I say is my understanding of reality, which may not be, of course, the same as the truth, but in mathematics, at least you can check my math. The math should be right. Okay, so first things first. A lot of you are probably coming in for the first class. You're not sure what are we going to do? Should I stay for the full 10 classes? So right now, I want to give all of us an overview of what's going to happen over the next 5 weeks, give you a rough lay of the land of what topics are going to come when, and we'll go from then. So I would say that week one, we have the basics or preliminaries. And this includes something like Ito's lemma. I'm not going to prove Ito's lemma, I'm just going to show it. And really, I want this to be like a flow conservation. So you've seen all of this, you've seen flow conservation in when you're talking about stationary distributions for discrete time Markov chains. And really, this is the concept I just want to remind people of. Then we're going to talk about the drift method a little bit because Stein's method and the drift method go hand in hand. They're quite synonymous, really. I'm going to give you an understanding of what do I mean by the drift method, and this appears in the literature elsewhere. And lastly, Poisson's equation. Poisson's equation is it's the engine on which everything runs. This is the heart of Stein's method. And we'll understand it. I'll get you familiar with it to a certain degree. Okay, so that's week one. That's the basics. If if you've been in this game for 5 or more years, you probably know everything except maybe the Poisson's equations because that's a little bit more specialized. But definitely, if you feel like, yeah, I've seen this stuff before in week one, probably you have. Week two, and this is the core. This is really the core idea. I'm going to show you all of the steps that are used in Stein's method for diffusion approximations of queuing systems through a simple example, and we're going to have the driving example of an M infinity queue. So an infinite server queue. What is the result we're going to achieve? That the stationary distribution of the M infinity is approximately a normal 0, 1 when properly renormalized. And this approximately, I'm going to make this precise. Okay. And specifically, we're going to have a bound on the distance of these two distributions. And if you, again, have seen the infinite server queue, this stationary distribution is a Poisson. So what we're doing is we're showing that a Poisson and the normal 0, 1 are close in some sense. Okay. But the most important part about this driving example is, again, that this contains most of the features of Stein's method. And then if you want to apply this stuff to another model, um, you can do this. You can repeat the procedure. Okay, so that's week 2. Then we're going to have a little bit of a detour. I don't know if it's going to happen week 2 or week 3. We're going to have some like a note on high order approximations. This is not part of the core idea. This is just saying like the approximation we're going to consider here is going to be like 1 over square root of n accurate. Can we talk about 1 over n accurate approximations, etc.? Okay, so a little detour. And then we're going to go back to week 3. And this is the core again. So let me call this the dual method. So this is the pre-limit approach to Stein's method, to the generator comparison approach. Um, I'm going to call week 3 also core. So if you only have 6 hours to devote to this class, I want you to attend these 2 weeks that I've circled. The methodologically, I want to compare this to the primal and dual approaches in linear programming, right? This is the most common way of thinking about Stein's method. And this, I want to say, this is the primal approach. Now, in linear programming, once you go to the dual approach, your constraints suddenly go into the decision, into the objective function, right? Everything flips on its head. And that's also what happens in this pre-limit approach. Without saying anything else about it, without showing any more details about it, there's not much I can communicate about this other than this is the important stuff. Then we're going to have some multidimensional stuff, multidimensional dimensional models. So all the difficulty is in multidimensional models in this methodology, really. Lastly, we're going to talk about I'm going to give it non-Markovian. I'm going to use quotation marks because I'm going to explain what I mean right now. So non-Markovian models, again, for those of you who have been around a little bit, when I say non-Markovian models, I think most of you will think about, oh, models where things are not exponentially distributed, like models when the service time is not exponentially distributed. But non-Markovian is not accurate because you can always augment the state space with some extra information to make the model Markovian. But basically, I'm going to talk about how to extend this stuff to settings where the primitive parameters are not exponentially distributed. This is cutting edge research-wise, whereas the rest of the stuff, probably week number 2, has been around for 40 years almost. Okay, and lastly, depending on how things go, right? This is like trying to predict the weather. I'm pretty sure what's going to happen in the first 2 weeks. I'm not very sure what's going to happen 5 weeks out. So let me not try and predict this. If we have time, we'll go into Stein's method for mean field approximations. Okay, good. So again, I hope that you understand now when to show up. But really, the class is designed to be like this, give you an extra tool in your probabilistic toolbox. Okay, that's that. Quick overview, because I can't, with good conscience, talk about Stein's method without doing this one first. Okay, so what is Stein's method? Okay, so let's talk about the simplest setting that we know of in terms of limit theorems. x1, xn are IID, mean 0, variance 1. Of course, we can renormalize everything. Sorry, variance sigma squared, not variance 1. So we have that the sum xi from 1 to n divided by, and this is where I'm going to make a mistake maybe, of course. So I mean the standard central limit theorem scaling minus the normal 0, 1. And right now this is not rigorous. Okay. If I want to look at the distance between these two variables, so maybe I have a distance dk, and dk is the Kolmogorov distance. So the Kolmogorov distance is basically probability x is less than or equal to little z minus probability y less than or equal to little z, and we take the supremum over all z in R. And I define this to be the Kolmogorov distance between x and y. So now it's rigorous. There's a result from the 50s. There's going to have the third moment, and we're going to have it divided by square root of n, and we're going to have a constant like 0.48 something something something. Okay, so if Rich, like, you don't need to answer this, but do you recognize this? Have you ever seen what this is? In fact, this result is called the Berry-Essane theorem. And this is proved sometime in the 1950s. And maybe the constant, I don't remember the history of the constant, maybe the constant was sharpened since then. But the point is, if you want non-asymptotic results about the distribution of a sum of IID random variables and comparing it to a normal 0, 1, this was the first of its kind. Okay. And that's in the 50s. However, the approach, the proof technique, crucially needed IID. Okay. If we introduce any sort of dependence, even weak dependence among the xi's, then the proof breaks down. It's very sensitive. So what are we going to do? In 1972, Charles Stein published a paper, and this is basically repeating this result, but without necessarily the IID assumption. And what was special about the approach of Charles Stein was that it was fairly generic. It didn't really need to focus on the fact that these were IID random variables. And so this gave hope for um, a broader approach, that's a more generic approach that can be used to establish these kind of quantitative error bounds in the setting of limit theorems. Okay, so Charles Stein used, well, he didn't call it Stein's method, I'm sure, but what he did was eventually called Stein's method for the normal approximation. So what I'm doing right now is I'm giving you some historical context so that you can appreciate what we're going to discuss in this course. All right, so there's Stein's method for the normal approximation. Crucially, the normal distribution is the limit, right? So there's some, I'm going to call this the pre-limit. This holds for any finite n. When the limit is a normal, Charles Stein developed the machinery for that. Okay. Then again, maybe so the sequencing of things, the sequencing may be off, but Louis Chen was the PhD student of Charles Stein, and Louis Chen developed Stein's method for the Poisson approximation. So specifically, when the limiting distribution is Poisson, in fact, the approach here is known as the Stein-Chen method. Okay, So the fact that they share a name when it comes to the Poisson approximation tells you something. It tells you that going from normal limiting distribution to Poisson limiting distribution, there was a non-trivial jump or gap. And then after Lewis Chen, basically what we're seeing in the world of Stein's method is people are saying, well, okay, we can do Stein's method for normal approximation, for Poisson approximation. What about exponential approximation? What about binomial approximation? What about, all right, what about all of these approximations? And then people start coming up with these ideas of how do I take the spirit of Stein's method and apply it to these different settings um, when I have these different limiting distributions. Okay. And the course largely, what we're going to cover these 10 weeks largely goes back to this 1988 paper by a man called Andrew Barbour. By the way, um, this isn't that old. So Charles Stein passed away perhaps about 10 years ago, but Andrew Barbour is alive, and Louis Chen, I believe, uh, I haven't been up to date, but I'm sure he's alive as well. So this is recent stuff, and the people are still around and active academically. So anyway, Andrew Barbour came up with the setting where the limiting distribution is the stationary distribution of a Markov, let's just call it Markov chain, right? Um, the setting there was a continuous time Markov chain with a discrete, with a countable state space, but the idea of connecting Stein's method to stationary distributions of Markov chains, or more broadly Markov processes, goes back to 1988 to Andrew Barbour. Um, good. And this method is called the generator comparison approach. And the generator comparison approach is what this class is about. Now, I cannot give you a great idea of what happened in the Stein's method literature post 1990 because it is pretty big. It's quite big actually. I'll give you a sense. The community around Stein's method, if you go to one of these conferences, you'll see like on the order of 100 people attending this. Um, and it's studied all over the world, Europe, Australia, East Asia, everywhere, USA. Okay, so the generator comparison approach allows us to compare stationary distributions of two different Markov chains. All right, so that's it in terms of history. I've given you about 20 minutes of it, and let me go into the math. Okay, so first, this is what I'm going to call stationary equations. Uh, I call them stationary equations. You can think other names include rate conservation laws, flow balance equations. I honestly don't know what the best thing to use here. So number one, we have Ito's formula in multidimensional Euclidean space. So this is going to assume some knowledge about stochastic differential equations on your part. So suppose I have a process, a stochastic process that satisfies the stochastic differential equation, dt, plus sigma y of t dw of t, where w of t is a RD dimensional standard Brownian motion. And for those of you who are not familiar with stochastic differential equations, let me not leave you behind. So let me cross out this term involving Brownian motion. If I write down a process y that satisfies this equation, dy is equal to b of y of t dt, this is like an ordinary differential equation, and this gives you the dynamics or evolution of the process y, right? And b is going to be the drift of these dynamics. If I uncross out the Brownian motion component, all this is saying is that the stochastic process y is going to have a deterministic component plus a random component. And the random component is going to be driven by Brownian motion. And this term in front of the Brownian motion, you can think of it as like the volatility or the variance. This is responsible for saying how much of the effect is due to the randomness versus how much of the effect is due to the deterministic part. Okay, so I have to be precise. So B is a map from RD to RD, and sigma is a matrix valued map, so that this actually is a vector or equation of vectors. Suppose B and sigma are nice, sufficiently regular, okay? If you really want to see what this means, go check out definition 4.1.1 of this book, Bernd Oxendel. So I just want this to be fully self-contained. But that definition gives you a couple of like very low-level technical conditions. In a little bit, maybe next class, I will talk about sufficient conditions on B and sigma in order for this definition to be satisfied. And those sufficient conditions are going to be like B and sigma are Lipschitz, basically. Okay, so think about B and sigma being Lipschitz. If I have a function C2 on RD, this is what Ito's lemma says. It says that f of y of t minus f of y0 equals, okay, now let me just write this down. It's integral from 0 to t. I'm going to have delta I, this is the partial derivative. Plus 1 to d partial I partial j f y of s d, and this is the quadratic variation component. Okay, and everything is inside the integral ds. All right. If you don't remember what quadratic variation means, that's fine. This is going to be the final formula I want you to focus on. Sum from 1 to d, partial I, f of y of s, bi y of s. Remember, b is a vector, so bi is the component, plus 1/2 sum I comma j, partial I, f of y of s, Yes. Okay. And lastly, 1 to D, 0 to T. This is the Brownian motion component. Okay. And sigma I is the row vector. Ith row of the matrix sigma. Okay. All right. Let me divide this part into two components. So first thing, I want to take everything inside the first integral. I'm going to call this g sub y of f of y of s. Okay. And the g stands for generator. So indeed, this is the infinitesimal generator of this stochastic differential equation. This part, let me call this just star. Notice that this is an integral with respect to Brownian motion, so it's going to be a martingale. And we're going to use the property that it equals 0 in expectations. Okay, so suppose further that, number one, the function f is such that this star term is a martingale. Number two, the process y of t has a unique stationary distribution. And from now on, I'm going to call stationary distribution just SD. And denoted by the vector y. So y is the random vector having the stationary distribution. And three, the function is y integrable. So this expectation is finite. Four, the generator applied to this test function is integrable itself. Okay. Then what happens? My claim is, let's go back over here. If I initialize the initial condition according to the stationary distribution, and if I take expectations with respect to the stationary distribution, then the expectation of the left-hand side equals 0 because of stationarity, and because we assumed that the function is integrable. And on the right-hand side, this second term is going to equal 0, the expectation of it, because this is a martingale. And we're going to be left with, so let me write it down. What we're going to be left with is 0 equals the expected value of the integral from 0 to t, g f y of s ds. And now this is where property number 4 comes in. I would like to interchange the expected value and the integral ds, and the integrability condition number 4 allows me to do this. Finally, this is just t times the expected value of gy f of y. Okay, and this equals to 0. And then since t is arbitrary and we can divide both sides by t, what this is really saying, so Ito's lemma says much more than this, but Ito's lemma implies that expected value of this infinitesimal generator applied to some test function equals 0. Okay. And this is what I really care about. I can call this rate conservation or stationary equation, but I'm going to use another term, basic adjoint relationship, or BAR. Why am I using bar? Because it's the quickest to pronounce. Okay. Um, but I want you to remember basically what Ito's lemma boils down to for us is this basic adjoint relationship. Okay, that this holds for all sufficiently regular functions f. Good. Now, if you haven't seen this bar before or Ito's lemma before, let me state it again in the setting where you are more familiar. Okay, where you may be more familiar with it, and that is the setting of the CTMCs. Bar for CTMCs. Okay. So now, so before you do this, I forgot to do it. Um, there are many ways to think about Ito's lemma, and this is the way I want us to think about it. Ito's lemma, for the purposes of this course, is basically a version of the fundamental theorem of calculus, right? So suppose, let me just zoom in way over here and make the writing smaller. So suppose I had a deterministic process, x of t, okay, and this evolved according to some deterministic dynamics. Then f of x of t minus, pardon me, that doesn't even have to be x of t. Simply have a function f of t minus f of 0. By the fundamental theorem of calculus, this is equal to, and suppose the function is differentiable, okay, I can write down this difference as just one integral, the integrating over the derivative. Ito's lemma for us is going to be a version of the fundamental theorem of calculus, except what is the complication? The complication is that these functions depend on random variables, right, or stochastic processes. And that is where the quadratic variation term comes in. If it wasn't for the quadratic variation term, we would have basically the fundamental theorem of calculus. Okay, so that being said, same thing. We're going to do the same thing for CTMCs. Suppose that x of t is a continuous time Markov chain on a countable state space. S with a unique stationary distribution given by pi. So pi, this is a row vector. Okay, we have probability of being in state 1, probability of being in state 2, etc. Okay, now what I want to achieve is also a kind of fundamental theorem of calculus for CTMCs. So motivation. If we have f of x of t minus f of x of 0, and we have the expectation conditional on the initial condition, can I write down the fundamental theorem of calculus? In this case, yes. We have the generator g x g of f of x of s ds. Okay, and this is not rigorous right now, so don't worry about it. This is just like some informal motivation. And if I take x naught to be distributed like the stationary distribution, I arrive at expected value g f of x equals to 0. Okay, and that's where we're going. All right, so let G be the transition rate matrix of the CTMC. Okay, so this is the transition rate matrix. It tells you with what rate do you jump from state I to state J. What do we know about stationarity? How is pi related to G? Okay, pi G equals 0. This is, this is again the first class in Markov chains you had. You say, if I want to solve for the stationary distribution, I need to solve the system of linear equations. Okay, so that much we know. Now, any function f from the state of our countable state space, so S to R, let's say S is state space of the CTMC. And can be thought of as a column vector. Okay, what do I mean by that? So typically the the Markov chain can take on, oh, sorry, yes. How do we prove the uniqueness of the stationary distribution of that? This is outside the scope here. What is it? Irreducibility. So in the case of stochastic differential equations, I'm just going to point you to it. Pick up a book and look into that. But uniqueness is not within our the scope of this class. Okay, so any function can be thought of as a column vector. Why? Because we can, again, enumerate the countable state space. So let's say our states are x1, x2. The Markov chain can take on values x1, x2, x3. And then I have f of x1, f of x2, f of x3, dot, 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 right? I can enumerate all of the possible values of f and store them as a column vector. Okay. Now we consider expected value of the generator. Let me label it g sub x. G sub x of the function equals, or what does that equal? We want to show when does it equal 0? Well, this is simply G, the matrix applied to the column vector, multiplied from the left by this row vector, the stationary distribution. When does pi GF equal 0? Okay, this is the question we want to answer because, again, this, or rather, this is what I'm going to call the BAR, basic adjoint relationship. And it equals 0. So let's see. Number one, if the state space is finite, if there's only finitely many elements, then pi GF is the sum, okay, over all elements x, y in the state space, pi sub x, g x y, f of y. Just take a look at this and convince yourself this is true. And of course, we have the double summation here. But since we only have finitely many elements, we can rearrange the summation in any sequence that we want. And so we have the sum. What do we do first? The y's. f of y sum over all the x's pi x g x y. Okay, but this term equals 0 because pi g equals 0, right? In other words, when the state space is finite, it's trivial the fact that this term equals 0. And that is achieved by rearranging the order of summation to multiply. Basically, we want to multiply pi times g first, and then we want to multiply it by f instead of pi multiplied by g times f. Okay. Now, and this is an important technical lemma. If I have the lemma. Now, this appears Glynn, and just to give you a reference, Glynn and Zevi 2006, I believe. But as I was writing my PhD thesis, I noticed this appears earlier on in Shane Henderson's thesis, actually, 1996. But I'm sure that people have been using it forever as well. But I'm just giving you 2 pointers. If if the state space is infinite, countable but infinite, if this sum pi x, the diagonal elements of G, and the absolute value of x is finite, then pi g f equals 0. Okay, and another way to interpret this thing is basically the expected value of the diagonal elements of the matrix multiplied by the value of the function. And we take absolute values here, and then we with the understanding that x is distributed according to pi, this thing should be finite. Okay, so basically to verify the BAR, you just got to verify this condition holds. What's a good way to think about it? Usually your Markov chain, your transition rates will belong to one of two cases. Either the total transition rate is going to be bounded by some constant. For example, okay, so by the way, this is the statement of the lemma. Example, MM1, in the MM1 queue, the transition out of any state is bounded by lambda plus mu. I'm being super informal here, right? But the transition out of any state is basically bounded by a constant, so that this condition boils down to verifying the integrability of the test function f. However, in M infinity, we have a arrival rate lambda, but we also have a service rate mu times the number of customers in the system. So this is the case where the transition rates cannot be globally bounded. So it's not just about verifying the integrability of f in this condition anymore. That is really the nuance. That's all. Okay, now since I did say we're going to be thorough, I want to give you a proof. Okay, so first of all, let me show you this one, right? This equation, or these two equations, they don't really use the fact that S is finite, except for using the Fubini-Tonelli theorem to rearrange this double summation into summing over the y's first in the x later. So to apply the same equality, all we need to do is double check that the Fubini-Tonelli theorem assumptions hold, and namely that this sum here is absolutely summable. Okay, so that's what we're after. Once we verify that this thing is absolutely summable, We're done. So look, x, y in S, pi, g, x, y, f of y, and this equals, okay, sum over the y's first, f of y. I'm going to split the inner sum into two things. I'm going to sum of all the x's that don't equal y. And I'm going to do gxy multiplied by pi of x. Now, quick thing to notice, the transition rate matrix is only negative on the diagonals. So on the off diagonals, I don't really need these absolute values. Now on the diagonal terms, g pardon me, plus g y pi of y, y comma y. I do need the absolute value on the diagonal terms. Okay. Sum f of y, sum of the off diagonal terms, and sum over y, f of y, g y y, pi of y. Okay. Now, what is this equal to? So this is basically doing the y is fixed. Okay. So this is a row vector. This is like the left inner product of pi and the column of g. Since pi g equals 0, this thing equals absolute value g of y, pi of y. Okay. And realizing that, the two terms actually become identical. 2 times the sum over y, f of y, g y y, I y. Okay. And we're done. Why are we done? We are done because our assumption was that this, which is the same sum as we have below, that this thing is finite. Now, if this is finite, we just shown that it implies that we can use the Fubini-Tonelli theorem, and then the proof of for the finite state space holds. Okay. Good. Shouldn't right-hand summation have, yeah, you're probably right. Yeah. So second to last line, have a GYY. Are you talking about this thing, Izzy? Absolute value. Oh, yeah, absolute value. So I'm a little bit, yes, thank you. Yes, absolutely, yes. Throw in the absolute values everywhere. Thank you, Izzy. Okay, so quick takeaway. Takeaway. For Ito diffusions on RD, and this is unconstrained, that's the key thing. On unconstrained Euclidean space, we have expected value generator applied to a test function equals 0. This we call the basic adjoint relationship. For CTMC on countable state space, we have expected value gx f of x equals 0. Of course, not for all functions. We just visited some conditions that we need for this to hold, but this is going to be the BAR. Okay. And then the same thing can be extended to basically other stochastic processes. So specifically going beyond CTMCs to models with general primitive distributions. But for the first 4 weeks, this should be plenty for us. Okay, so remember the bar. Also, quick word, if we need to, I'll bring it up then, but we could have constrained diffusions. What's the simplest example of a constrained diffusion? So this is one-dimensional space. This is the time, and this is the stochastic process. It's called reflected Brownian motion, so it behaves like Brownian motion does in the non-negative space, but it's never allowed to be negative, so it's reflected at the boundary. And this is an example of a constrained diffusion where Ito's lemma has to be modified to account for basically local time at the boundary. Okay, this is an extension, and the methodology and the framework can go in that direction as well, but not the best topic for an introductory class on this stuff. Okay, so now I'm going to go to the drift method. Probably extends to jump diffusion processes, as I'm sure it does. Yeah, I'm sure it does. Okay, so the drift method. How am I doing on time? It seems like I'm doing better than I thought. All right. So we spend a lot of time working on the bar. And before we, in queuing, if like me, right, so I did my PhD, I started in 2012. By then, people have moved past largely, right, the question of stability, say, and people have really been chasing down this question of steady state, limited interchange, and looking at justifying all these diffusion approximations. And as a PhD student, I found it curious that I myself am going after these very difficult properties or problems or processes without really understanding what can be done to the original queuing model you're analyzing, perhaps. So I'm going to motivate the drift method as basically saying, now that we have the bar, what can we do with it in order to recover performance metrics of interest in my queuing system? Okay. And the drift method refers to taking the bar of the queuing model. Number one, try different test functions. F and try different test functions and observe what they give you. See what you get about CTMC or performance metrics of interest. So example of 1,000 word example is worth 1,000 words. Okay, so let me jump into one right away. And this is as simple as it gets, really. But if you've never seen the drift method, this is a great introduction. So the CTMC has the generator, a single server queue. And this is going to have the generator. Let me use Q. With rate lambda, so lambda is our arrival rate, we get one extra customer. And with rate mu, we have a departure as long as there is somebody in the system. So this Markov process tracks the total customer count, number waiting plus in service. Okay, now given this generator, so I'm going to consider first f of q equals q. I'm going to keep calling this a test function. You can call it a Lyapunov function, sure, but I think Lyapunov function, in my mind at least, it's useful more for drift inequalities, whereas this, I don't, not really a big deal, to be honest. Okay, if generator f of q equals 0, so again, capital Q is the random variable having the stationary distribution, then, so we're going to be forgiving on this, we're going to assume this holds. And now we want to plug in our test function. Now our test function is linear. F of q equals, so with rate lambda, it's going to be q plus 1 minus q, which is, of course, just equal to 1. And mu, expected indicator q is positive. I'm going to have q minus 1 minus q. And this equals to -1. And what I get from it is that lambda equals mu times the probability that the queue is not empty. Okay. This is basically Little's law. Okay, the rate of inflow, and it's going to be the service time times the average number. No, not the average number. I take that back, sorry, not Little's law. Okay, or probability Q is positive is lambda over mu, and this quantity is known as rho, which is the system utilization. Great. Well, that's nice, but again, we should be careful. This is a rigorous course. When is this condition true? So we're going to go back to our lemma that we proved, and we're going to say, okay, true if expected value g q comma q absolute times q itself is finite. Now the generator, right, there's only one arrival rate and a single service rate. So the generator actually is bounded by lambda, the diagonal elements are bounded by lambda plus mu, less than or equal to lambda plus mu, expected value of q. All right, so basically, in order to be allowed to use this test function, we need to verify that the first moment of the queue length is finite. Okay. Now, this is the MM1Q. There are probably a million ways to show that the first moment is finite in the MM1Q, but I don't want to use anything else other than the bar. Okay, so this is, I want to claim that the bar, BAR, is self-contained. Okay, that it gives you everything you need about the stationary distribution. So I don't want to resort to other things. So what I'm going to do here is I'm going to say how to use f of q equals q without proving without proving that the first moment is finite. Okay. And this is a common argument. Answer, truncation. Truncation, we consider f of q instead as q truncated m. So this is the minimum of q and then m. All right, let's apply the generator to this test function. It's going to, of course, depend on m, but I'm going to omit that. Now, does this test function satisfy the bar condition? Yes, it does, because we saw in the MM1Q, you just need integrability of the function, and the function is truncated, so it's bounded. So it does satisfy the bar. Q, okay, lambda. All right, now let's see. I have Q plus 1 minimum in M minus Q minimum M. And right away, I want to break it down to, it basically boils down, you got to break it down to two cases, okay? And the two cases to consider are if Q is less than or equal to M minus 1. What happens if Q is less than or equal to M minus 1? This is Q, and this is Q plus 1 times 1 plus indicator Q is bigger than or equal to M multiplied by M minus M. So this part is equal to 0. And then mu, indicator Q is positive, or rather I should say, and of course, I need lambda times the expectation here. And I have the expectation show up everywhere. Indicator Q is positive. Okay, so here is going to be Q minus 1 minimum M minus Q minimum M. And this is going to be divided into indicator Q is less than or equal to M. Now, if Q is less than or equal to M, basically this is Q and this is Q minus 1. So we get our negative 1. And if Q is bigger than or equal to M plus 1, we get 0, M minus M. So let me just summarize everything that I've written. 0 equals lambda probability Q is less than or equal to M minus 1. This is from this part. Minus mu probability 0 less than Q less than or equal to M. And now, of course, we say lambda PQ less than or equal to M minus 1 equals mu probability QM, okay? And now we have the monotone convergence theorem. So these things are, these converge to 1, this converges to probability that Q is bigger than 0, and we recover our original result. Okay, so I'm showing you this because the truncation method is extremely powerful. It holds. I haven't seen an example where it doesn't hold. What do I mean by that? I haven't seen an example. For instance, if using a linear test function gets you some result, then using the truncated linear test function and taking m to infinity will get you the same result. And I personally haven't seen a model or a system where this is not true. Okay, although I'm sure they exist, and it's just my limitation. Anyway, now you know how to use a truncation. Well, let's see what else we can get out of the BAR. Okay, so this performance metric of interest was on the probability that the server is busy. We may want something like the expected number of customers in the system. How do we get that? Well, the answer is we have to try a different test function, okay? Not just linear one. And after a little bit of thinking, if I left you on your own, you would say, okay, maybe how about I try f of q equals q squared. Now we're going to assume we know that the second moment is finite. I don't want to go through this truncation argument again. It's a little messy. Not messy, it's a little bulky. Let's just see what the bar gives us. Then, number one, let me not apply the expectation. Let me just look at the generator. Q plus 1 squared minus Q squared plus mu, and the Q is bigger than 0. Q minus 1 squared minus Q squared. And some light algebra. I think it's useful to be a little slow here because this type of argument is very common. And so it pays to be a little bit slow with the derivations. And all right, so got rid of the q squares. And now I want to collect the terms that have a q in front of them, and then I want to collect the terms that don't. So I got 2q of lambda minus mu indicator that q is positive, and lambda plus mu indicator that q is positive. All right. One more thing to note. The indicator is going to be pesky. But the nice thing is, if q equals 0, then this part equals 0. So the whole term is killed. In other words, we can get rid of the indicator. A lot of the times it's this indicator that will give you trouble. Okay, so this is what the generator equals. Taking expected value, we get 2 lambda minus mu expected value of q plus lambda plus mu probability of q is bigger than 0 equals 0. So now, and remember from using the linear test function, we know what this is actually. This is equal to lambda over mu, this probability. By the way, I forgot to mention this, but it's important to point out. All of this, the drift method relies on the fact that there is a stationary distribution, that the system is stable. Okay, so I didn't say this explicitly, but I've been using it everywhere, that lambda is strictly less than mu. So the question when we're working with the drift method or Stein's method, we're assuming stability, right? And stability there's a lot of effort to showing that systems are stable. So we're going to stand on the shoulders of those people who did this and paved the way before us. We're going to assume stability. Okay. Rearranging, we have 2 lambda over 2 lambda minus mu. And this is going to be, I think, rho over 1 minus rho. And that should be the familiar one to you, right? Okay. So look, we've discovered a way to get access to the first moment of the Q length. What about expected value of Q squared? Answer, use a cubic Lyapunov function. So this paradigm in the world, in the literature in the world, it holds if a linear function or a quadratic function gives you something, then you can increase the power to get access to higher moments, for example. Okay. Sometimes the caveat is sometimes a quadratic function won't give you access to the moment, and we'll see that shortly. Okay, so we have an expression for basically any moment. That's nice. To justify the finite second moment assumption, we can use truncation, or we can bypass the need to justify it using truncation. But it's messy. So question, and this is still all related to the drift method. By the way, don't think I ever said it. Drift method, if you hear about it, it means look at the generator, pick a test function, and set the drift to 0, or take expectation with respect to steady state, and you get basically these equations. For every test function you choose, you get an equation. And the drift method, the philosophy of it is to pick nice test functions to manipulate the equations and derive performance metrics of interest. Okay. How to verify without or in general? Answer: foster the Lyapunov drift condition. Okay. So what I'm going to show you is extremely powerful. It's used a lot in practice by almost everyone I know who works in this. This comes from theorem 4.2 of Mine and Tweedy, 1993. The paper is called Stability of Markov Processes 3. Okay. So given a CTMC or Ito diffusion, we'll call it X, and the function V of X, which is non-negative, with V blowing up as long as X goes to infinity itself. So this is not just one-dimensional, right? This can be multi-dimensional, such that GV of X is less than or equal. So the generator, when applied to this Lyapunov function V, satisfies this inequality. I'll break it down in just a moment. Then X of t is positive Harris recurrent. The function f itself is integrable, and we have an upper bound on the function f. Okay, So this is extremely useful. Again, this is more for the people that haven't seen it. This is an extremely useful and powerful result. What does it say? So if you go to the paper, it holds, or the setting they consider is far more general than just CTMCs or diffusions. Okay. The reason I basically parsed their theorem into our setting because we are going to be considering CTMCs or Ito diffusions. Okay. If you can find a function v, so v is usually up to you to find. Start with quadratic, for example. And if the generator applied to some v can be decomposed into these two terms for some, let me just add, K is a compact set. So if the Markov chain has a negative drift, except potentially on a compact set, okay, and the F and the G here are non-negative, that's key. Then then we have stability, we have positive Harris recurrence, and actually the expected value of F is finite, and we have an explicit bound on it. So the best way to internalize this lemma is to apply it to our MM1 example. Remember, we said, moment. Remember we wanted to show that the first moment is finite when we use the truncation argument. Let us try to show that the first moment of the MM1 system is finite using this Foster-Lyapunov drift condition. Okay, so as I said, let us try v of x or v of q. This is q squared. And the other thing to note, nowhere here do we have to assume, yes, nowhere here do we have to assume that v is integrable. And thank you, Yang. F, let's see. No. I got confused. If you're in K, F, F is less than negative epsilon. So the question is, do we need to assume that this thing is less than some negative epsilon outside of K? My answer is I believe I copied the theorem correctly. Take a look in the paper by mine and Tweety. And again, I believe I copied the theorem correctly. And I don't need this negative epsilon exactly, but that's the place to double check. Okay. Okay. So we have this test function. And remember, we have our generator. So let me go back here. And I'm just going to copy paste because we already did all the hard work for the generator. I want to reuse it. Okay. And I don't care this time about the intermediate steps. Okay. So this is a generator. Remember, we have lambda less than mu. So this thing is negative. Okay. This is the positive part. Right away, I want to do this. So I want to do q lambda minus mu plus, sorry, I want to make the negative explicit. Q mu minus lambda minus q mu minus lambda. So far, this holds with equality. The inequality is I'm going to get rid of the lambda, and I'm going to get rid of the indicator because that is just messy. Okay, so we have G, and this should be GV of Q, V of Q. Okay, now, what is the problem? The problem is that 2 mu is, of course, dominated by these negative terms, but Q has to be big enough. So I split the term as I did, because I would like the circle term to be responsible for killing the 2 mu, or for exceeding the 2 mu. When does this hold? Let K, our compact set, be the Q such that mu, or mu minus lambda, is Q is less than or equal to 2 mu over mu minus lambda. Okay, so when we're outside the set K, we have mu minus lambda times Q is bigger than negative, is plus 2 mu less than or equal to 0. Okay, so we pick our compact, so we say on the compact set, we can have messy things happen. Outside of it, we need negative drift. And what do we have? Okay. For Q not in K, GV of Q is less than or equal to negative Q mu minus lambda. Okay, so that means that for all Q, so GV of Q is negative mu minus lambda Q minus mu minus lambda Q plus 2 mu. This is less than or equal to negative mu minus lambda Q if we are outside of the compact set. And then if we are in the compact set, we have this term. Okay, so again, outside of the compact set, this thing is negative. But inside of the compact set, the generator is bounded by at most 2 mu. As a result, expected, and I want to make this explicit, this thing equals our f of q, and this thing equals our g of q. As a result, expected value of q is finite, and we actually get the bound. Expected value of q is less than or equal to 2 mu over mu minus lambda. Okay, and this is within a factor of 2, approximately 2 rho over 1 minus rho. So even though it's an upper bound, it gives you the right order of magnitude. There's some value to that as well. Okay, I think this is a good place to stop for today. Let me just give a brief summary of what we've covered and where we're gonna go next. So we started off with Ito's lemma and the BAR, right? BAR for Ito diffusions, BAR for Markov chains. Remember those, they're gonna stick with us all the way. Then we went to the detour and said, okay, given the BAR, how do I turn it into something useful? And this is where the drift method comes in. Okay. Shown you the drift method. Usually we start with linear or quadratically up enough functions. We unlock some performance metric of interest in the system. We need to be careful about the finiteness or integrability of our test functions. And as another tool, I gave you the Fosterly up enough drift condition. Um, let's see. Okay, where are we going next time? So next class is going to be concluding the preliminaries. I'm going to talk about using exponential test functions. This is referred to as the transform approach sometimes. I'll show you an example where the test function doesn't give you anything. So in MM1, we can get everything about the system, but even if we go to the GG1, even something as simple as the first moment is not accessible to us using these test functions. And then I will conclude by talking about the Poisson equation. And the Poisson equation is going to be the last element of these preliminaries, and it's going to set the stage for the generator approach. Thank you all. Thanks, Ziv.
All right. Thank you, Anton. So, so yeah, we still have a couple minutes if anyone has any sort of last questions. And otherwise, we'll see you all Thursday. All right. See you then.